All right, welcome to this introductory session of machine learning on Spark. How many of you have written applications on Spark? How many have already used MLlib? Oh, good, most of you are in the right room. In this session, I will show you the basics of doing machine learning on Spark using MLlib. If you have written applications on Spark, you probably appreciate the ease of use of the data frame APIs and the power of it. Well, MLlib features the same elegant design. It's also very easy to use, and it's highly scalable. So we will start by looking at an example in R. Data scientists typically use Python or R to do machine learning. At the moment, there are way more algorithms developed in Python and R than in MLlib. However, they typically don't scale beyond a single machine. MLlib, on the other hand, scales by distributing not only data, but also algorithms. We'll then introduce a few key concepts in MLlib, and finally, we will implement the same example in Spark. Hopefully, by the end of this session, you'll be interested to try machine learning on Spark yourself if you haven't already. So the example we're going to look at is to predict the remaining useful life of a certain type of aircraft engines. You can think of the life of an engine can be measured by the number of cycles. And a cycle is a flight that the engine takes. An engine can only make so many flights before it has to go into maintenance. So the problem we're trying to solve here is to predict how many cycles an engine has left, given how many it has already gone through, and certain sensor readings from the engine. The data is publicly hosted on the NASA data repository. There are 3 input files: the training file, the test file, and the labels corresponding to the test data. So let's take a look. Here's the R code. Now you don't need to know, is it big enough? You don't need to know R in order to follow. I will explain what it does. This first cell is just to reading the training data. So this file contains data for 100 engines, all of the same type. Each row contains the engine ID, a particular cycle in that engine's life, 3 settings, and 21 sensor readings from the engine at that particular cycle. Now we need to do some processing before we feed this data to machine learning. First of all, not all the columns are relevant to our prediction. Let's say in this case, only 4 sensors are relevant. Sensor 9, 11, 14, 15. And the number of cycles that the engine has already gone through is also irrelevant. So these are the input to our machine learning model, and we call them features. Now in this case, we also need the desired output to our machine learning model. And the desired output is the known remaining cycles of the engine. So how do we compute it? We find the max cycle that's seen in this file for each engine, and then we simply subtract the current cycle in each row from the max cycle, and we get the remaining cycles. So now the training data is in the right shape. We got our features, and we got our label. Next, we're reading the test data. So the test file is exactly the same format as the training file. So we also need to do some processing on the test file. So we extract the necessary features for our machine learning model. For the test file, we can also get rid of all the rows except the row that contains the last seen cycle for each engine, because there's no point of making predictions in previous cycles. So now our test data has all the features, but where's the label? The label comes from the third file. The third file is just a single column that contains the known remaining cycles corresponding to our test file. This is sorted by engine ID, and if you notice, our test data is also sorted, so we can just combine them together. Now we get our features and our label for the test data. So now we're ready to do machine learning. I'll talk a little bit more about how to choose a machine learning algorithm later, but for now, let's say we take this gradient boosted regression model. So we're telling the model which column is our desired output and which columns are our features. And we set some parameters here. Later on, you will see we call these hyperparameters. And then we fit this model on our training data, and what we get out of it is a trained model. So how do we know how good is this model? In order to do that, we apply our trained model to our test data to get the predictions. And then we compare our predictions with our label. Remember, the label is the known remaining cycle. It's the known good answer. So we compare it with our label to see how close they are. In this case, the metric we're computing is root mean squared error. Now, if this error is small enough, maybe you can declare this model is good enough and take it to application. Or if it's not good enough, then you go back to tune your model by changing the parameters, maybe try another model, maybe collect more data to retrain your model. So while this is a very simple example, it does represent the typical machine learning workflow. You start by preparing your data, shaping it into the format that's ideal for your machine learning. Then you train the model on your training data and evaluate the model on your test data. If the model is not good enough, you go back to retrain it. If it is good enough, you take it to production, but that's not the end of it. You need to collect the feedback from production and provide it back to the beginning of your workflow to continuously improve your model. How fast and how well you can do this experimentation, take the model to production, and provide feedback to your system is really becoming the competitive advantage for many businesses. Because the better your model, the more customers will come to your business. And the more customers, the more data and the better data. Data is most important here, and it takes time to accumulate. Machine learning cannot do much without data. So if you look at the documentation in MLlib, the algorithms are slotted into a few categories. Classification algorithms are used to predict categories. There can be binary classification, is it spam, is it not spam? Or multi-class classification, what kind of iris flower is this? Regression algorithms are used to predict numerical values, like the example we have seen. Now, classification and regression are typically what we call supervised learning, meaning you are providing the desired outcome when you train the model. Clustering algorithms are used to group similar items. For example, if you have a collection of shapes of different colors, different sizes, you can pass it to the model, and the model could group it by size or by color or by shape. Collaborative filtering is typically used in recommendation engine. So people who are similar to you likes this movie, therefore you are probably going to like this movie. And frequent pattern mining can be used in anomaly detection or basket analysis, like people who buy dry dog food typically also buy wet dog food. Now, these last three categories are typically what we call unsupervised learning, meaning when you train the model, you're not providing any correct answer, any desired outcome. The model will explore the pattern by itself. While this helps to identify which type of algorithm to use, not all developers are deeply trained in all these algorithms. So which algorithm should I use? You can find algorithm cheat sheet like this one online. This one is for Azure Machine Learning. There's also one for SAS and a much more elaborative one for scikit-learn, but I didn't find one for MLlib. So you start from this middle node and you make a decision. Are you predicting value, or are you predicting category, or are you doing anomaly detection? Let's say if you predict category, then is it 2 classes or is it 3 or more classes? If it's 2 classes, then you end up in this bottom right rectangle, which has all the binary classification algorithms with a little description that differentiates this algorithm from the others. Now, in reality, algorithm selection requires a lot of expertise and domain knowledge on your data and the problem you're trying to solve. But for beginners, this could be a good place to start. So there are a few key concepts in MLlib. The first one is transformers. Transformers take a data frame and transform it into another data frame. But the kind of transformation it does is not the same kind that you typically do like in the SQL API. It's specific for machine learning. So for example, if you have a text field, well, machine learning cannot deal with text. It needs to be converted to a numeric field. So you could use string indexer or one-hot encoder, which are both transformers, to convert it to numeric values. Or in this case, let's say I have a column that represents sensor 1 and another column represents sensor 2. You cannot feed it directly to machine learning algorithms. It needs to be converted to a single column of vector. So how do you do that? You create a vector assembler and you take this data frame and you transform it. The output is a single column of vector. And this is just Spark's representation of vector. The first field, 1, means it's a dense vector. The second field means how many elements are in the vector. The third field means the index of the elements. Because it's a dense vector, it's not used here. And the last field contains the actual values for the elements. Another concept is estimators. Any machine learning algorithm is an estimator. So in our case, we will use the same machine learning algorithm as we used in R, and that's the gradient boosted tree regressor. So we have our training data with features and a label, and we fit the regressor on this training data, and the output is a trained regression model, which is a transformer. Because the transformer takes a data frame, so it can be the test data or the new data, and the output for the transformation is the prediction. And finally, a pipeline is just a series of transformers and estimators chained together that describes your machine learning workflow. So now let's see how we can implement this example in Spark. So first we need to prepare our training data. So this is just the raw format in our file. And what we need to do is to extract the features, just the necessary columns, and to compute another column which represents our label. Now this part has nothing to do with machine learning. You can just do it with data frame APIs. So here, we're just reading in the training data file. We find the max cycle grouped by engine ID, and we add a column, which is our label, by subtracting the current cycle on each row from the max cycle to get to the remaining cycle. And then we just select the features we wanted. So now the training data is in this shape with our features and with our label. So if we go back and we remember, you cannot just feed those data frame with multiple columns, with multiple features to machine learning models yet. You need to convert it to a single column of feature vector. So how do we do that? We create this vector assembler, and we tell our vector assembler, these columns are our features, and this is what we want to call the output column. So the output of this is a single column of feature vector that contains all your features. Now we're ready to create our regressor, and we tell the regressor which column has the desired output and which column has our features. Now, instead of applying these two separately, we create a pipeline that contains both stages. And finally, we fit this pipeline on our training data. So the output is a trained model. And what does this model look like? If you print it out, use the toDebug string, you will see in this case, because we're using a tree, it really is just multiple trees represented by gigantic if-else statements. So if you look at the code here, so we created the assembler, we created a regressor, we created a pipeline that contains our assembler and the regressor. We fit the pipeline, our training data, and finally we get the model, and we print the model out, which is gigantic if-else statements. So next we want to evaluate our model. But before we can do that, we need to prepare our test data. So this is the raw format of our test data, and this is the label for our test data. Again, we need to do some processing to get our features and combine with our label. This part doesn't have anything to do with machine learning, just the data frame APIs. So here we can see we're reading the test data, we find the max cycle grouped by engine ID, then we get rid of all the rows except the row that contains the max cycle. We sort the test data by engine and get only the needed features. Then we're reading the third file, the label file. The label file is already sorted, so now we can combine the test data with the label, and now our test data is also in the format that we wanted with features and the label. So the next thing we can do is to evaluate our model. So how do we evaluate our model? Because we already created that pipeline, and our model is a trained pipeline model, we can just use the trained pipeline model to apply on our test data to get the predictions. Then in order to evaluate the model, we compare the prediction with our label. Remember, the label is the known correct answer. So we created this regression evaluator. We tell the evaluator which column is our correct answer, which column is our prediction, and what is the metric we want to compute. And we get the metric. So in this case, we also compute the root mean squared error. And here's the code. Now let's say this error is still too large, and we need to tune the model. So Spark also provides a few mechanisms to tune the model. One is called hyperparameter tuning. Hyperparameters are those parameters that you provide when you train the model. So for our gradient boosted tree regressor, there are a bunch of hyperparameters, but here are three of them. The max iteration, the maximum depth of the tree, and the step size, typically called the learning rate. So you can build a grid of this. And what Spark will do is to train the model on each permutation of this grid. So in this case, it will be 10, 5, 0, 1, 10, 5, 0, 2, 10, 10, 0, 1, and so on. So it would be 3 by 2 by 2, 12 permutations. Now, if you just do that, you risk something called overfitting, meaning the algorithm works very well on your training data, but is not general enough to work well on new data. So in order to help solve that problem, Spark also supports cross-validation. So what cross-validation does is you create a cross-validator, and you tell the cross-validator what is your pipeline, which one is your evaluator, what is your parameter grid. But you also specify number of folds. So what is number of folds? In this case, let's say number of folds is 3. And what this means is for each permutation of that parameter grid, it will further divide the training data into 3 folds. So it trains on the first and second folds, and then tests on the third one. Then it trains on the first and the third, and test on the second one. And then it trains on the second and the third and tests on the first one. And then it computes the mean of that error metric to represent the performance of this particular permutation of parameter. So now you can see your 12 permutations needs to be timed by 3, becoming 36 permutations. So model tuning is a very heavy operation. And fortunately, Spark knows how to distribute it. So here's our model tuning code. We created a parameter grid, and we create our cross-validator, and then we fit our training data, fit the cross-validator on our training data to get to the model, and use the trained model to make predictions on our test data, and then we calculate our root mean squared error. Now you can also access the best model found out by the cross-validator and print out its hyperparameters. Now let's assume this model is good enough. So we want to save it. So saving the model in Spark is very straightforward. It will be saved in Parquet format. The only reason you would want to save it would be because you want to load it somewhere else. So here's a sample, very simple sample example of structured streaming using the model we just saved. So this first line loads back the model we just saved, and then we define our stream. In this case, it's just files inside a folder, and then we apply the model on our streaming data to get the predictions, and we write the predictions into a memory sink. Now, because we write it in a memory sink, you can easily use a SQL statement to explore the data. So here, let's say we pick engine 42, and we want to see how does the prediction trend as this engine goes through its life cycles. So at least here we can see as the engine ages, the prediction does decrease, so which should be the way. So now this is good if your application is also a Spark application. What if you want to run prediction, let's say on an IoT edge or something that doesn't have a Spark cluster? You have a few options. You can save the model in a format called mleap. So it's a serialization format as well as an execution engine. If you save it in that format, then you can load it back into your Java application and run it there without any dependency on Spark. Databricks also has a library called ML Model Export. So your data scientists can store the model in Python, and then you can load that model back in your Spark or Java application, again, without any dependency on Spark, although not all models are supported yet. So both these formats are in JSON rather than Parquet. All the notebooks here can be accessed at GitHub, and there are a few more links related to the example we have. I hope this was helpful. Thank you very much.
Excellent. We have time for several. Oh, can you go back one slide to the links? Oh. Thanks. We have time for some questions. Over here.
Thank you for your talk. So I have two questions. First is, what's the best way to select the best features from your raw data? Because let's say I have 100 features, and I want to find like correlation, which ones are more important than the others. So is there a good machine learning algorithm for selecting features? And secondly, how do I decide that, okay, the regular machine learning algorithms are not working and I need to make a leap to, let's say, deep learning? So what's the point of the pivot that a developer has to decide based on the data?
Okay, so the first question was how to select the features. That really requires some domain knowledge as well as a lot of experimentation. So you can explore your data to see if one feature works good or not. It's even, I don't know if you know this, like even after all the hyperparameter tuning and cross-validation I did, the root mean squared error only reduced a little bit. So the tuning actually is very hard work and requires a lot of expertise. I don't know if there's an automatic way to help you with that, to select the features. And the second question is, how do you know if the algorithm is not good enough and you have to do deep learning? This also, basically the way you evaluate an algorithm is to compute some metrics. And if we didn't talk about deep learning here because MLlib doesn't have anything for deep learning. And there are a lot of other talks. And deep learning typically is used in like image recognition or natural language processing. And sometimes you can combine those algorithms together, like not just one algorithm. So again, it's a matter of experimentation.
Yeah. Does Spark apply automatically feature normalization?
Feature normalization?
Yeah, normalizing the features.
I don't think there's any automatic way to do it.
Okay,
Yeah.
so you must do it explicitly. I mean, in the example, I didn't think you normalize the features, right?
Like by normalizing, you mean?
I mean, for example, you may have features which have a range going from 1 to 100, for example, others going from 1 to 5, and maybe you want them to have.
Yeah, there is some transformers that can do that. Yeah, you can check it out. I don't know on top of my head, but.
Okay,
yeah.
Thank you.
Hi, good presentation. I have this problem. I was wondering if you could provide any suggestions. It's something related to frequent mining, so an unsupervised problem. An unsupervised problem, unsupervised learning, I should say, and it's based on anomaly detection. Now, I do have, is there any way to convert that or maybe design a certain architecture that would somehow feed it back and say, okay, you know, this is semi-supervised, I have detected an anomaly, this is confirmed, and is there any suggestions you could go around like making it unsupervised to somewhere semi-supervised?
I have a little bit of a hard time hearing you, but we can talk maybe outside the room. I suppose the next speaker will need to be here too.
Hi, nice talk. So my question is, can MLlib models be fitted on a structured streaming, or it's only on a, like, can I train the model on streaming data using Spark SQL?
Sorry, I didn't get that.
Let
me talk to you offline. Yeah.
Okay.
All right, I think that, well, we got one more here.
Thank you for the talk. So today we talk about how to use MLlab, right? But we do have some other algorithm not exist in MLlab, which are potentially traditional, some like for example, scikit-learn library, they have some other algorithms. If I want to deploy a not parallel compute algorithm in Jupyter, not Jupyter Notebook, but Databricks Notebook, should I follow this same pipeline?
So is your question like you have a bunch of algorithms that's not developed in MLlib?
Right.
And
how can I elaborate those?
Yeah, I mean, in that case, it's kind of similar to what they usually do with like deep learning algorithm these days. You can still do parameter tuning in a more distributed way, but the algorithm itself is not distributed. So the difference between MLlib is the algorithm itself is distributed.
And I can deploy it in the same way, although the algorithm itself is not parallel compute.
Yes. Yeah.
But I can use, let's say, a Databricks notebook, and then I import that library in that notebook, and then run the algorithm
Yeah,
over
so if you check out a few sessions that when they talk about deep learning, how to do deep learning in Spark, it will be the similar approach.
Okay.
Yeah.
Okay. Thank you.
Because TensorFlow algorithm itself is also not distributed among different nodes, but you can still leverage Spark to do hyperparameter tuning.
Excellent. Let's have one last round of applause for our speaker.